In this segment, we'll finish up our discussion of Markov chains by looking at the uniqueness and stability of invariant distributions. We'll start by recalling the definitions of irreducibility and aperiodicity, and we'll see how these are linked to the uniqueness and stability of invariant distributions. Then we'll look at an alternative approach to uniqueness and stability based on something called the Dobrushin coefficient, and along the way we'll look at a bunch of examples. Now recall that we defined a Markov chain to be irreducible if for every pair of states I and j, there exists some number n such that you can reach j from I in n steps. And we defined the period of a state I of a Markov chain as the largest common divisor of the set shown on the slide, and this is the set of all numbers n such that you can reach I from I in n steps. And we said that a chain is aperiodic if all states have period 1, and we also showed that all states have the same period, so if any state has period 1, then the chain is aperiodic. Now we'll establish an important properties of chains that are both aperiodic and irreducible. Now if you have such a chain, for every pair of states I and j, there exists some number n0 that depends possibly on I and j, such that the transition probability from I to j in n steps is positive for all numbers n larger than n0. Now the proof depends on a standard result in number theory, as you'll see. First note that for any state j, the set of integers n such that pjjn is positive is closed under addition. Now what this means is that if you have two integers in this set, then their sum also belongs to this set. For example, if you can reach j from j in 2 steps, and you can also reach it in 5 steps, then you must be able to reach it in 7 steps. And furthermore, this set must have largest common divisor 1 by definition, since we're talking about an aperiodic chain. Now here's the result from number theory that we're going to use. Any set with these properties, so any set of integers that's closed under addition and has largest common divisor 1, contains all integers above some threshold n1. So for any such set, there exists some threshold n1 such that all integers larger than n1 are contained in this set. Now given any two states I and j, choose some integer r such that you can reach j from I in r steps with positive probability. There must exist some such r because the chain is irreducible. Now we'll set n0 to equal n1 plus r and consider the transition from I to j in n steps. Now pijn must be greater than or equal to the product of pijr and pjjn minus r, because this product gives you one set of ways in which you can reach I from j in n steps. Now each term in this product is positive. We chose r such that pijr was positive, and we know that n minus r is greater than n1, and every number greater than n1 is contained in the set of integers n such that you can reach j from j in n steps. So we've shown that pijn is positive for all n sufficiently large. Now think about what we've established here. We've shown that if the chain is aperiodic and irreducible, then for every pair of states there exists some threshold such that if n is larger than this threshold, then no matter what its value, you can reach I from j in n steps. And since there exists such a threshold for every pair of states I and j, we can take the largest of these thresholds, and for any n larger than that, you can transition from any state I to any other state j in n steps. Now if you think about this, you should be able to see that it has the following implication. If you think about two different realizations of this Markov process, starting from two possibly different states, there's a positive probability that regardless of where these two realizations of the process began, they're going to end up after n steps in the same state. And so the probability distribution over all future states for these two realizations will end up being the same. And that's the intuition behind the following result, which states that a finite Markov chain that is irreducible and aperiodic has a unique stationary distribution pi star, with each component of pi star being positive, and furthermore the probability that you will be in state j after n steps, if you start in state I, is just pi star of j. In other words, it's independent of I. And we saw this numerically for the Bernoulli-Laplace model, where we saw that each row of the transition matrix ends up converging to the same distribution, and that distribution is in fact the invariant distribution. By the way, I'm using invariant distribution and stationary distribution interchangeably here. Now to get some more insight into the conditions for uniqueness and stability, let's consider an alternative approach based on something called the Dobrushin coefficient. So given a Markov chain with state space S and transition matrix P, the Dobrushin coefficient alpha of P is defined as shown on the slide. Now let's think about what this definition means. It says the following: take any two rows I and j of the transition matrix. Starting with the first column, look at the entries in these two rows and pick the smaller one. Then do the same for the second column and the third column and all other columns. And then add up all the entries that you've picked. This will give you a number for the pair ij. Now do this for all possible other pairs ij and you'll get a set of numbers. Take the smallest of this set of numbers and you have the Dobrushin coefficient. Now the best way to understand this is with some examples. So let's go back to the Bernoulli-Laplace model with r equal to 4, and you can verify that the transition matrix is as shown in the slide. If you're at a boundary state, you leave it with probability 1, otherwise you can move up or down one step, or you can remain where you are. Now let's think about how we'll compute alpha of P, or the Dobrushin coefficient for this matrix. Let's start with the first two rows. In the first column, the entries are 0 and 1/16. The smaller entry is 0, so we pick that. In the second column, the entries are 1 and 3/8. The smaller is 3/8, so we pick that. And in the remaining columns, the smaller entry for these two rows is always equal to 0. So the number we obtain for the first two rows is 3/8. Now let's look at the first row and the third row. We're going to do the same thing for this pair. For the first column, the smallest entry is 0. For the second column, it's 1/4. For the third, fourth, and fifth column, again we have 0. So the number we get in this case is 1/4. Now let's look at the first and the fourth row. In this case, for the first column, the smallest entry is 0. For the second, it's also 0. And in fact, for the third, fourth, and fifth, it's also 0. So we get 0. Now once a 0 appears in this set, we know that the minimum of all numbers must be 0. And so therefore the Dobrushin coefficient for this matrix is in fact 0. But if you look at the same model, but second order transitions, you see that the Dobrushin coefficient in this case cannot be 0. And that's true because if you look at the third column, every entry is positive. So for any pair of rows, you're going to get a positive number when you reach the third column. So in this case, since there exists a column such that the entries in all rows are positive in this column, the Dobrushin coefficient is strictly positive. Now let's look at the coefficient when we have multiple ergodic sets. Here you can compare the second and the third rows and see that the Dobrushin coefficient is clearly 0. And this is true not only for P, but in fact for every higher order transition matrix as well. So no matter what power of P we take, the Dobrushin coefficient of P to the n is going to be equal to 0. And this is true in this case because we have multiple ergodic sets. Now let's look at periodic Markov chains. So here's our earlier example. Again, look at row 2 and 3, and you see that the Dobrushin coefficient for P is equal to 0. And you should be able to verify that for higher order transitions, no matter what n happens to be, and whether it's odd or even, the Dobrushin coefficient for P to the n is equal to 0. Now for all finite state Markov chains, the Dobrushin coefficient must lie between 0 and 1. It must be non-negative because we are adding non-negative entries. These are probabilities we are adding. And it must be less than or equal to 1 because P is a stochastic matrix. The sum of any given row is equal to 1. So if you're looking pairwise and picking the smaller element of two rows, the sum of those can't possibly exceed 1. If you have a Markov process that is irreducible but not aperiodic, then the Dobrushin coefficient is equal to 0 for every higher order transition matrix. And the same is true if you have multiple ergodic sets. In the Bernoulli-Laplace diffusion model, we saw that the Dobrushin coefficient for the transition matrix is 0, but we also saw that the matrix for second order transitions has a positive Dobrushin coefficient. Now we say that the rows Pi and Pj of the transition matrix P overlap if there exists some column K such that the entries in these rows are both positive. And you can verify that the Dobrushin coefficient for a matrix P is positive if and only if every pair of rows overlap. Now it should be clear to you that if there exists any number n and any state j such that the nth order transition probability from I to j is positive for each state I, so j can be reached from I for every I in n steps with positive probability, then the Dobrushin coefficient alpha of Pn must be positive. Now let's link this to uniqueness and stability. So as before, we define capital Pi as the set of distributions on our state space. For any two distributions pi and pi prime in this set, we define the distance using the D1 metric as we did before. This is just the sum of the component-wise distances between the two distributions. Endowed with this metric, pi is a metric space, and the pair pi p is a dynamical system. And we can think about uniqueness and stability of rest points of this. And here's the main result. A finite state Markov chain with transition matrix P has a unique and globally stable stationary distribution if and only if there exists some number n such that the Dobrushin coefficient of the matrix P to the n is positive. So there's an equivalence between a Markov chain that is irreducible and aperiodic and one that has a higher order transition matrix with a positive Dobrushin coefficient. And you can verify uniqueness and stability either by checking for irreducibility and aperiodicity, or by verifying that there exists a power n of p such that the corresponding Dobrushin coefficient is strictly positive. And this gives you two different ways of trying to verify whether a finite state Markov chain has a unique and globally stable stationary distribution. And I'll stop there for this segment.